question that our hypothesis needs to answer is, does the marble lose energy as it travels? Okay. So remember from our previous notes, okay, remember that, so we've got our roller coaster, and let's just draw like some kind of roller coaster here. If energy is conserved, PE1 should equal KE2 at the bottom of each slope. Potential energy and kinetic energy. We derive this equation from that energy equation. The final velocity is the square root of 2 times height times 9.8 meters per second squared. VF, final velocity. Pardon? Yeah, remember little g is acceleration due to gravity for all objects on Earth in the absence of air resistance. It's 9.8 meters per second squared. So the important thing here, right, is that if your marble travels from here to here, so from here to here is the distance the marble travels. Now, obviously, if I use a tape measure, I can get this little curve in here too. It's important that I try and make this measured correctly, okay? This is a little like model of that. So that's the displacement, okay? And we talked about in last class, if the slope is straight, acceleration should be constant on an individual slope, okay? Which means, okay, that so displacement, so S is displacement. Okay, and velocity average velocity is displacement divided by time. And if acceleration is constant and the marble starts at 0, so you measure each velocity independently. Okay, in other words, right, with my stopwatch, I'm like, start, stop. And I'm only measuring one slope at a time. Okay. Then I know that VF also equals 2 times average velocity. The final instantaneous velocity of the marble on one slope is going to equal 2 times the average velocity that I calculate. You have to like you have to time it from looking at. You have to like see it. Well, like so if this was my roller coaster, and I was like, and I would really want to watch it. I want to go start, stop, right? Which, does that seem great? I could also, when I'm doing my individual slopes, I could also put something here. It either makes it easier to see. So like, as I was looking at it, I was like, maybe a piece of tape. But something else I could do is maybe I could put something there that I can hear when it hits the bottom of the slope. Right, but that's a very important thing. That's gonna like, to get good data, you're gonna want to do something to make it easier, because you saw how fast that was. It's like maybe 0.1 seconds or something. It's gonna be difficult to time. Okay, so this is the height. So h right here is this height. From here to here. So this would be like h1. That's the height of the first slope. That's the displacement of the first slope. This, so be careful, it's got to go, your height has got to go from the peak to the trough of that specific slope. So this would be h2, and this would be displacement 2 from here to here. And then this would be height 3. And this would be displacement 3. Okay. So the question we're asking is, does the marble lose energy as it travels? Last class, somebody brought up a force that they thought might take energy from the marble. And I don't remember who it was, because that was last week. Yeah, force of friction. Somebody said force of friction might be taking energy from the marble. So a plausible idea here is that the force of friction is taking energy from the marble. So I'm going to jot that right here with the hypothesis. Is something you want to think about when you write it. You should do that too. We're gonna write it down right here. Like, is the force of friction? Okay, this is going to help you compose a hypothesis. Is the force of friction taking energy from the marble? Okay, so now remember from last class, and I know this energy stuff is all new. If energy is conserved, that is when the potential energy the marble has at the tippity top is going to equal the kinetic energy that the marble has at the very bottom. If energy is not lost at all, the potential energy the marble has at the top is going to be equal to the kinetic energy the marble has at the bottom. And that's what this formula assumes. If this marble has this final velocity, right? This is the velocity you would have, the final velocity you would have if energy is not lost. We'll do a standard deviation from now on. And then we'll do a percent deviation of that standard deviation. Especially with numbers like this, like that's the only thing that's going to give us meaningful error. Okay, so if energy is not lost, then this is the velocity we calculate from energy equations, kinetic and potential energy equations. Okay, the velocity should be equal to this or greater than this. If energy is not lost, velocity should be equal to or greater than this number. Equal to, great. Should it ever be greater? No, okay. So if your velocity ends up being greater than this number, you know that your measurements are wrong. Okay, that's. If energy is conserved, yeah. Oh, it's a G. It's a lowercase g with an arrow above it indicating it's a vector. It's acceleration due to gravity for all objects on Earth. Okay, so if the marble gets its energy from the height, okay? So one way of testing whether energy is conserved, right, is to see if is to measure time and calculate average velocity and then take 2 times the average velocity and see, is this less than or equal to this velocity? You follow? So we can test, and I want you to test, we can test if energy is lost by comparing our measured and calculated average velocity on each slope with the average velocity calculated from the energy equations. Okay, so we have one way to mathematically test whether or not a hypothesis that makes a claim about energy being lost is verified. Okay. There is a second way to test this hypothesis. And that is experimentally and observationally. So, question. And before I say this, does everyone see that this model is the same as this drawing? Okay, this is the actual, what something would look like. And this is the same, these are the same values here, okay? So I'm gonna take a photograph of the model and make sure it gets into our materials, right? To help us like plan our design. Oops. All right. Okay, now this is tricky. Can anybody tell me a way you could construct this roller coaster so that it would only function where the marble goes all the way through if energy is conserved? A way you could construct a roller coaster so that the only way the marble goes all the way from the start to the finish is if energy is conserved. So like it's the same matter of like a straight line. Say it louder. If every slope is the same height, can you help? Yeah. But hold on. So have you ever heard, you know those perpetual motion machines? Yeah. Right? The thing that they do is they conserve enough energy that it looks like energy is not being lost. So I could do another example. If I was to drop a bouncy ball from here and it comes all the way back up to my hand, it would mean that energy was perfectly conserved, right? if it bounces and it doesn't come all the way back up to my hand, energy was lost when it hit the ground because it didn't have enough energy to make it all the way back up. Okay, so grab the end. Okay, so what Eli said is one way we could test if this thing conserves energy would be if we made each slope the same height. Now, obviously, we're sort of doing this on the fly. So we're going to kind of guesstimate. Well, yeah, but I mean, you know, not on Earth. We want to test it, don't we? Yeah. Well, I would say unless you can get zero friction, right? It ain't gonna work. Yeah. Or in the case of the ball, only if the ball is perfectly elastic. Yeah. Meaning it doesn't deform at all, and all of the energy is transferred instantly into its motion. So a pool ball, a bowling ball, these are balls that were designed to keep momentum, keep energy. Further down a little. Move this down. Down, down, down. Wait, hold on. Okay, screw that up. Yeah, let's just do 2. But I think here, let me just hit the. Does this look about the same height? Remember, angle of slope doesn't matter. The path it takes doesn't if it's the same height. Hey. How's it going?
I think you must have
Oh yeah, of course. Join us.
I remember doing this. I did this at home.
All right, this was the first virtual.
Yeah.
Yeah.
I put it on my wall.
All right.
So much, isn't it?
All right, cool.
Okay.
All right, that's bad boy. Okay. All right, so do we understand here that if energy is conserved, the marble is going to do what? It's going to make it all the way up to the top of this slope. Still going to lose that. Well, if it maintains energy, it's going to go faster, 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 maximum velocity, slower, 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 and faster, 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 right?
Yeah.
Whoops. Aw. So what did I do here? What am I doing with the slopes here? Each one, right? Each hill is decreasing in height.
Yeah.
This height is smaller than this height. This height's actually bigger, but I didn't put really any hill here. This hill was high enough to get me over this little tiny thing, right? Okay. So so one of the things you have to do when you build a roller coaster is first thing you have to do is build a coaster so that a marble makes it down 3 slopes, up 2 slopes, all the way from the beginning to the end without stopping. Check, done, okay? If you can do it this way, you can demonstrate that energy is conserved. But I probably made you feel like that's a waste of time when Eli and I came up with this idea of having the slopes the same height, and it just doesn't work, right? So somebody tell me in words how this had to be designed in order for the marble to make it all the way through.
Acceleration stays constant. Does that mean the displacement would have to have less curvature for acceleration?
Yeah. I should make it better than that. But But talk to me about the heights of these and how I had to do it, why this didn't work and this did work. What do you got? So I had to make the height that precedes each hill higher, and they had to go down as it moves through the roller coaster. Because what was not conserved? Because energy is not conserved. Okay, so the point being here, there are two ways to verify your hypothesis. Way number one is by trying to make these as high as you can when you do it, and building it and explaining if I am correct and energy is not conserved, I will have to make each hill or each slope higher than the hill that follows it in order for the marble to be able to go all the way through, right? And if I am correct, my velocity calculated with the energy equations will be what, Bridget, compared to my measured velocity? The velocity, if I'm true about energy being lost but not conserved, will be less, okay? So there are two things you can say would happen if the marble loses energy. Bridget. Yeah, that would work, but it would also wouldn't defy the energy requirement of a marble losing energy. Yeah. It would keep most of its energy if you had straight areas instead of hills. Yeah. It would keep more of its energy. Well, it would be gaining energy. See, each height gives it more energy. And if I don't come all the way back up to the same height, I don't lose all of my energy. Right? And so, yeah, it's actually going, each slope is going to be faster. But the run all the way through the coaster is just to test the hypothesis and explain how you have to construct it and make sure that you can do it. That's the design challenge. Your test of the hypothesis, you're going to want to run on each individual slope. Because in order to use 2 times average velocity for final velocity, what 2 things have to be true? Lydia, in order to use 2 times average velocity for final instantaneous velocity, what 2 things have to be true? Initial velocity has to be what? It actually has to be a specific number. No, initial velocity, if like, yeah, it has to be 0. Yeah. I'm sorry, I didn't know you weren't paying attention, or that you lost attention slightly. I'm so sorry. I thought we're in the same plane. Yes, and then what has to be true about acceleration to use that? Acceleration has to be what? You don't know? You know. You were talking about it. Yeah.
Wait. Say your question.
Okay, in order to use 2 times average velocity, Lydia said initial velocity to find final velocity, instantaneous velocity, initial velocity has to be 0. So that's why you have to test each one independently. Otherwise, you don't even have math for it, right? And then what has to be true about acceleration while it's traveling? Acceleration has to be constant, right? And so that's what you were talking about. This isn't really straight enough for me to say acceleration is constant on this, right? I need to try to make this a little straight at least, right? But given what you were talking about with timing, as long as my velocity isn't higher than the velocity calculated here, I'm at least verifying reality in some sense, right? And not all of a sudden my marble's magically gaining energy from the universe or something like, Dr. Frank Taylor like shot some muons added or something. I don't know. Okay, so cool. Let's draw the second bit. So if energy is conserved, so the difficult part here is writing this damned hypothesis and giving me two ways that you can demonstrate it in words. And that's what we're going to spend the rest of the class doing. So if energy is conserved, this should work. In other words, a marble can travel all the way through. All right. If energy not conserved, all the way through. If energy not conserved, then H1 has to be greater than HA. I'm gonna go like HA. And H2 is gonna have to be greater than HB. And then finally H3. This is so messy looking. Oh, H3 doesn't, there's no. It's kind of weird, right? So what I'm trying to say here is the height of this has to be taller than the height of the hill it sets it up for. And then the height of this from here to here has to be taller than the height of this hill that it sets it up for, right, et cetera. I forgot where, physical reality was. Sorry, I was looking at the drawing. It's another physical reality, really just a model, not reality. Okay, cool. We need a break. I know, I'm sorry. And then we're gonna write hypothesis. So we're gonna take 5 and write hypothesis.